You are sitting here, looking at this screen, and yet, right now, in this very moment, hundreds of trillions of particles are passing through your body, every single second, through your bones, through your blood, straight through the earth beneath your feet and out the other side, without slowing down, without stopping, without you feeling a single thing. They leave no trace, they cause no pain, they cast no light. And perhaps the most unsettling truth of all is that almost nothing in this universe can stop them. These particles have a name. They are called neutrinos, the ghost particles, silent travelers passing through everything, noticed by nothing. You might think something so invisible, so untouchable, could not possibly matter, but you would be wrong, because neutrinos may carry the very answers we have spent centuries searching for, answers about how the universe was born, about the deaths of stars, and perhaps most remarkably of all, about why you exist, why matter formed at all, why the universe chose to become something rather than nothing. The ghost particles were here before the Earth. They were here before the Sun. Some of them have been traveling for nearly 14 billion years. And tonight, as you sit quietly, as the world around you slows, they are still passing through you, gently, silently, without a care. The universe is not empty. It is full, overflowing with things we cannot see, and the neutrino, this tiny, weightless whisper of a particle, is perhaps its most beautiful secret. Still traveling, still passing through, still waiting to be understood. The story begins not in outer space, not in some distant galaxy billions of light years away, but in a laboratory, a quiet, dimly lit laboratory in the 1930s. Scientists at the time were studying something called beta decay, a process where certain unstable atoms release energy and transform into something new. It seemed straightforward enough. Measure what goes in, measure what comes out. The numbers should match. That's the rule. That has always been the rule. But something was wrong. The energy didn't match. Not by a little, not by some small rounding error that could be explained away. The energy seemed to simply disappear. Not decrease gradually, not convert into heat or light or sound, just vanish into nothing. Now, in everyday life, things go missing all the time. Your keys, your glasses, your train of thought. But in physics, energy does not just disappear. That is one of the most fundamental laws of the universe, the conservation of energy. What goes in must come out, somewhere, somehow, in some form. And yet here it was, a hole in the ledger, a gap that no one could explain. The physics community was deeply unsettled. Some scientists quietly wondered whether the law of conservation of energy itself might need to be rewritten. Maybe the universe, at its smallest scale, didn't follow the rules we thought it did. Maybe energy really could disappear. That was a terrifying thought. But then, one physicist refused to accept it. His name was Wolfgang Pauli, and in 1930, he did something remarkable. He wrote a letter, not a paper, not a formal publication, a letter addressed to his colleagues that began famously with the words, "Dear radioactive ladies and gentlemen." In that letter, Pauli proposed something almost outrageous. He said, what if the energy isn't disappearing? What if something is carrying it away? Something we simply cannot see? He imagined a particle, a tiny, ghostly particle, one that carried no electric charge, one with almost no mass at all, one that passed through matter as if matter weren't even there. No trace, no signal, no footprint, just gone. It was, by any measure, a strange idea. Pauli himself admitted he wasn't sure it was right. He called it, somewhat reluctantly, a desperate remedy, because proposing a particle that, by definition, cannot be detected felt more like giving up than solving the problem. And yet, the idea was too elegant to ignore. If such a particle existed, it would explain everything: the missing energy, the unbalanced equations, the ghost in the data. The Italian physicist Enrico Fermi heard the idea and immediately saw its potential. He incorporated it into a full theory of beta decay. He even gave the particle its name, neutrino, Italian for little neutral one, small, neutral, invisible. And for the next 2 decades, it remained exactly that, a theory, a mathematical ghost, a particle that physicists believed in but had never actually seen. Because here is the astonishing thing about neutrinos. Every single second, trillions of them pass through your body. Right now, as you sit here, trillions of neutrinos, produced by the nuclear reactions inside our sun, are streaming through the Earth, through the walls of this room, through you, and coming out the other side without disturbing a single atom. They don't slow down, they don't bounce, they don't interact. They simply pass through, as if you weren't there, as if the entire planet weren't there. A beam of neutrinos could travel through a wall of lead 1 light-year thick, and most of them would make it to the other side. That's not a metaphor, that is literally, physically true. So how do you catch something like that? How do you detect a particle that ignores everything? It took until 1956. 2 physicists, Clive Cowan and Frederick Rines, set up a detector near a nuclear reactor in South Carolina. They filled large tanks with water. They surrounded them with sensors. They waited. Because neutrinos are so abundant, and the detector was large enough, that even at the almost impossibly low interaction rate of neutrinos, occasionally, very, very occasionally, one would collide with a particle in the water, and when it did, it would leave a faint, brief flash of light, a whisper of evidence. After months of careful observation, they found it. The signal was real. The neutrino existed. 26 years after Pauli's desperate letter, the ghost had finally shown itself. Rines sent a telegram to Pauli that same day. Pauli reportedly replied, "Everything comes to him who knows how to wait." But the story doesn't end there, because as physicists began studying neutrinos more carefully, they discovered something even stranger. Neutrinos come in different types, different flavors as physicists call them. There's the electron neutrino, the muon neutrino, the tau neutrino, and neutrinos change between them. As they travel through space, they oscillate, they shift from one flavor to another and back again, like a coin spinning in the air, neither heads nor tails, until it lands. This phenomenon is called neutrino oscillation, and it has a profound implication. For neutrinos to oscillate, they must have mass. Even if that mass is almost nothing,
the tiniest sliver of a gram. It must exist. And this matters enormously, because the original standard model of particle physics assumed neutrinos had no mass at all, zero. The discovery of neutrino oscillation, confirmed definitively in 1998, meant the standard model was incomplete. There is physics beyond what we know. There are answers we haven't found yet, and the neutrino, this invisible, ghostly, almost nothing particle, is pointing us towards them. So the next time you sit in sunlight, remember you are being passed through. Trillions of messengers from the heart of the sun, 8 minutes of travel, 150 million kilometers, streaming through you right now, silent, invisible, unstoppable. Each one a tiny echo of a 1930s mystery, a desperate letter, and a universe that still has secrets left to share.
Close your eyes for a moment, just for a moment, and imagine this. You are standing outside. The sky above you is gray and heavy, and it begins to rain, softly at first, then steadily. You feel it on your shoulders, on your hands, on your face. The rain is real because it touches you, because water, like almost everything in our world, interacts. It lands, it soaks, it leaves a trace. That is how we know the world around us, through interaction, through touch, through cause and effect. But there is something falling through you right now that you will never feel, not ever. No matter how still you become, no matter how quiet, it passes through you as though you are not there at all. This is the neutrino. Imagine standing in a storm, not a rainstorm, a neutrino storm. Every second, every single second you are alive, approximately 100 trillion neutrinos from our sun alone pass through every square centimeter of your body. 100 trillion every second. Through your skin, through your bones, through the soft and intricate machinery of your heart. And you feel nothing, not a whisper, not a tremor, not the faintest suggestion that anything has passed through at all. Because neutrinos do not interact with you. They do not interact with almost anything. They are not stopped by flesh. They are not stopped by steel. They are not stopped by mountains. They are not even stopped by the earth itself. Let that settle for a moment. The planet beneath your feet right now, this vast ancient ball of rock and iron and molten fire, is to a neutrino little more than a gentle suggestion, a mild inconvenience. At this very moment, the sun is below the horizon, and yet neutrinos born in the core of that star are traveling upward through the entire body of the Earth and emerging through the ground beneath you and passing through you from below, up through the soles of your feet, through the length of your body, and out the top of your head, having passed through a planet without slowing down. Perhaps this makes more sense with another image. Think of a billiard table. You lean down, you take your shot. The cue ball rolls across the green felt and strikes another ball with a clean, satisfying crack. Both balls move, energy transfers. The table accounts for everything perfectly. Now imagine you take that same shot and afterwards you measure the energy, and something is missing. Not a little, noticeably missing. You look around the table. No third ball, no hidden pocket, no explanation. The energy is simply gone.
This, in essence, is what physicists encountered in the early 20th century. During a process called beta decay, the transformation of one kind of atomic nucleus into another, energy appeared to vanish. And in physics, energy does not vanish. It cannot. It is one of the deepest laws written into the fabric of the universe. Energy is always conserved, always accounted for, always somewhere. So if it appeared to be missing, there had to be a reason. There had to be a third ball, an invisible one. This was the realization that led Wolfgang Pauli in 1930 to make one of the quietly revolutionary proposals in the history of science. He suggested, nervously, reluctantly, almost apologetically, that there existed a particle no one had ever seen, a particle so shy, so reluctant to engage with the world that it could pass through everything and leave no mark, no footprint, no shadow. He proposed it not because he wanted to, he proposed it because the numbers required it. And for more than 2 decades, the neutrino was nothing more than a mathematical ghost, an entry in an equation, a placeholder for something that might not even be real. But it was real. In 1956, physicists Clyde Cohen and Frederick Rines set up a detector near a nuclear reactor, a source producing neutrinos in almost unimaginable quantities. And they waited, patiently, watching for the rarest of events, a neutrino out of the countless trillions streaming through their equipment every second, actually stopping, actually interacting, leaving the faintest trace of its passage, like a single raindrop in that impossible storm, finally landing. And it happened. The trace appeared. The signal was real. The ghost had substance. That day, a telegram was sent to Pauli himself. "We have detected neutrinos." He is said to have been moved to tears, because after 26 years, the invisible had been made, ever so briefly, visible. Now, let us return to you, lying still, breathing slowly, perhaps already drifting toward the edges of sleep. You are at this moment a kind of cosmic sieve. Neutrinos from the sun are passing through you. Neutrinos from distant supernovae, the violent deaths of stars many times larger than our own sun, are passing through you. Some of these particles have been traveling for tens of thousands of years, some for millions, born in cataclysms so enormous that the human mind cannot truly hold them, and yet arriving here, now, in this quiet room, and passing through you as gently and silently as a thought. There is something almost meditative about this idea. We tend to think of ourselves as solid things, bounded, contained, definite. We have skin, and inside the skin is us. But the neutrino reminds us that we are, in a very real sense, permeable, open. The universe passes through us constantly. We are not walls, we are more like windows, or perhaps gauze curtains in a summer breeze. The breeze moves through, the curtain barely stirs, and yet both things are real, both things are there. What neutrinos have taught us goes beyond the particles themselves. Because they interact so rarely, they carry information that other particles cannot. Most of what we know about the universe comes from light, from photons, particles that travel from distant stars and galaxies and reach our telescopes. But photons are social creatures. They interact with everything along the way. They are absorbed, scattered, redirected. The light from the core of our own sun takes tens of thousands of years to work its way from the center to the surface because it is constantly bumping into things, bouncing, redirecting, getting lost. But neutrinos born in the core of the sun escape in roughly 2 seconds. They carry with them a direct message from the heart of a star, unfiltered, uncorrupted, immediate. When we detect neutrinos, we are reading a message written in the most extreme environments in the universe and delivered to us intact, whispered across the cosmos. There are neutrino detectors buried deep underground right now, in mines in Japan, in the ice sheets of Antarctica, in laboratories carved out of solid rock beneath mountains in Italy and Canada. They are buried deep, not to be closer to anything in particular, but to escape the noise, cosmic rays, background radiation, the endless chatter of a busy universe. Down in the deep, quiet dark, the detectors wait, watching for that 1 in a trillion interaction, that single fleeting moment when a neutrino decides to say hello. So tonight, as you settle towards sleep, know this: you are not separate from the universe. You never were. The universe is moving through you right now in rivers of invisible light. Ancient particles born in the cores of dying stars, in the first moments after the Big Bang, in the furnace at the center of our own small sun, are threading through you silently and continuously. You are in a way a detector, not sensitive enough to feel them, but present enough to be passed through, to be part of the journey.